Hello, welcome to the course on microwave engineering. Dear students, in the last video lecture, we have discussed about pin diode. So basically, pin diode is almost similar to our PN junction diode, but the difference is that there is a one more layer, which is the intrinsic layer that exists between P and N material. And because of this intrinsic layer, the device can be used as a variable resistor in forward bias condition, and it is used as a capacitor in reverse bias condition. So that thing we discussed in the last class. Now in today's class we are going to discuss about one more solid state semiconductor device, which is Varactor diode. So what is Varactor diode? So basically Varactor diode is PN junction diode, and which is operated in the reverse bias condition, and it is the device whose capacitance value varies in accordance with the reverse bias voltage. Okay, so basically ये PN junction diode है और उसको हमें रिवर्स बायस मोड में ऑपरेट करवाना है, और जब भी ये रिवर्स बायस मोड में ऑपरेट होगा तो उसका जो कैपेसिटेंस वैल्यू है that is varies in accordance with the applied reverse bias. This diode is also known as a varicap or volt cap. Varicap means variable capacitor diode or volt cap, and the varicap derived from the combination of two words variable and capacitor. So as I mentioned, the capacitance value of this diode is varied by changing the reverse bias voltage. It means that it provides variable capacitance. Hence from this word variable and capacitor, the word varicap is derived. If you look at the symbol of this Varactor diode, then it is almost similar to the conventional diode, our PN junction diode, but here in order to show the capacitive effect or capacitance effect, there are two parallel lines are there. Okay, these two parallel lines basically indicate the capacitance or capacitive effect. Okay, this one terminal is anode, another terminal is cathode. Okay, now basically Varactor diode is formed by merging p-type semiconductor material with the n-type semiconductor material, because it is PN junction diode, and the semiconductor material that is used for P and N region is basically silicon or gallium arsenide material. Okay, so if we have the low frequency operation, then basic material would be silicon, and in case of high frequency field, the material will be gallium arsenide. Means if you would like to use this Varactor diode for microwave applications or high frequency application, the material should be gallium arsenide, and for low frequency application, or if you would like to use in the electronics as low frequency application, then the basic material would be silicon. So this is the typical structure or construction of the Varactor diode. Okay, so basically this is the PN junction. Here there is a PN junction, correct? So here there is a PN junction, P region and N region. The anode is basically taken from the P region and cathode is taken from the N region, and there is a mesa structure. Okay, so the anode terminal is basically molybdenum metal anode terminal, and cathode terminal is the molybdenum metal cathode terminal. An entire structure is basically enclosed in ceramic tube, correct? Okay, so this is a typical structure of this Varactor diode. Now as we can see from the figure, as I said, N region is connected, this N region is connected with the mesa structure, and through this mesa structure a molybdenum metal with gold plating is connected to the N region, which serves as a cathode terminal of the diode. Similarly, P region is also connected with the molybdenum metal. Okay, but here the connection is through the gold wire. Okay, as you can see, the connection between P region and molybdenum metal is through the gold wire, okay, and this will behave as a anode terminal. So upper molybdenum metal act as a anode terminal, this act as a cathode terminal, okay. And as I mentioned, ceramic tube or ceramic layer is used to enclose the entire structure, excluding the anode and cathode terminal. Means anode and cathode terminal is outside of this ceramic tube. Now let's understand the working of this Varactor diode. So as I mentioned, in Varactor diode it is operated in the reverse bias condition, okay. So Varactor diode is a reverse bias diode. So if you recall your basic electronics, then in order to reverse bias any diode, the p-type material or anode is connected to the negative terminal of the battery and cathode should be connected to the positive terminal of the battery, okay. So we have to make sure that the connection to the DC bias should be such that this diode is always operated in the reverse bias condition, okay. And more important to note, Varactor diode is basically manufactured to store the charge rather than the conducting current, okay. So if we apply the forward bias, then it will conduct the current, okay, but the main purpose to design the Varactor diode is to store the charge. And which device store the charge? Capacitor. And when this diode show the capacitive effect, when it is reverse bias, so what obvious, rather than operating this diode in forward bias, we have to operate the diode in the reverse bias condition, okay. So let's understand what will happen if we apply the DC bias to this diode. So initially, if we do not apply any bias or under zero bias condition, there exists thin depletion region between P and N type material, okay. So there exists depletion region, thin depletion region under zero bias condition, okay. And here we will only focus on the reverse biasing of the diode because we have to understand the working of the Varactor diode under reverse bias condition. So as we apply the reverse bias, then majority of both the P and N region, means which are the majority charge carriers in the P type material? Holes. And in N type material, electrons are the majority charge carriers. So basically, by application of this reverse potential, the holes and electrons start moving away from the junction, okay, as happens in our normal PN junction diode. So due to this, what will happen? Due to this, the majority carriers depleted from the junction, so the width of the depletion layer will increase, okay. मतलब जो holes and electrons है वो junction से दूर जा रहा है, मतलब the region becomes depleted of the carriers, okay, near the junction. So ultimately the width of the depletion layer will increase, okay. So in this case, as the width of the depletion layer is increased, then this two region, P region and N region, will behave as a capacitor plates, and depletion layer will behave as a dielectric material. So basically what will happen, if you look at this using diagram, then basically as we apply the reverse bias to this diode, then the width of the depletion layer will increase. So basically this is P region, this is N region, and in between there is a let me show the depletion layer. So this is the basically depletion layer, correct. So this P and N material behaves as a two plates of the capacitor, and this dielectric will behave as a this depletion layer between the depletion layer in the diode will behave like a dielectric material. Ultimately we can say that, in short, under reverse bias condition, this diode behaves as a capacitor, okay. So basically the capacitance that is formed at the junction due to reverse biasing of the diode is basically known as a transition capacitance. It is known as a transition capacitance, okay, and it is denoted by C subscript T. And as we know that capacitance of the capacitor is given by epsilon A divided by D. So what is the distance between two plates? So here this P region act as a one of the plate, N region act as a another plate of the capacitor, and this dielectric basically, this depletion layer, depletion region is basically act as a dielectric material. So here you can see the distance between the two plates, that is P and N region, is nothing but depletion layer. They are separated by the width of the depletion region. Let's say the width of the depletion region is W. Then we can replace this D by the W. Then in that case, the capacitance will become epsilon A divided by W, where W is the width of the depletion region. Okay. And one thing we already know, as we increase the reverse bias, if we increase this reverse bias, then width of the depletion layer will increase, and if the width of the depletion layer is increased, then capacitance value decrease. Okay, so we can say that from this we can say that as we change the reverse bias, the width of the depletion layer will change, and if the width of the depletion layer is changed, then capacitance is also changed. So ultimately we can say that with the variation in the reverse bias, the capacitance of this Varactor diode is changed. Okay, and this is the typical characteristic curve of the Varactor diode. Okay, so you can see from this, as we increase the reverse bias, the capacitance is decreased. So this x-axis represent the reverse bias voltage, and y-axis represent the capacitance, transition capacitance in picofarad. So basically capacitance is inversely proportional to the width. So as we increase the reverse bias, there is an exponential fall in the value of the capacitance with the reverse bias voltage. And the relation between capacitance and voltage is given by the equation Ct is equal to K inside bracket Vk plus Vr raised to n, where K denotes the constant that depends on the semiconductor material and fabrication method. Vk denotes the barrier potential of the diode. Vr is our applied reverse bias, and n is the constant that depends on the doping level of the material. So let me repeat, here constant K that depends on the type of semiconductor material and fabrication method. Vk is the nothing but it is the barrier potential of the Varactor diode, and Vr is the applied reverse bias voltage, and where n is constant that depends on the doping level, and usually the value of n is 1/2 for alloy junction, and it is 1/3 in case of the diffuse junction. Correct? So this is the typical characteristic curve of Varactor diode, and from this we can conclude that with increase in the value of reverse bias voltage, there is a exponential fall in the value of the capacitance. Okay, so ultimately from this discussion we can say that this Varactor diode is used as a variable capacitor diode. Okay, so means if we change the reverse bias voltage, proportionally its capacitance value also changed. Now what are the applications of this Varactor diode? So Varactor diode is used in television receivers as a resonant tank circuit. In resonant tank circuit, this Varactor diode is used as a variable capacitor. It also used in the radio receiver for tuning purpose. It also used in frequency multiplier in various electronic circuit. It is also used as a voltage control oscillator. So in voltage control oscillator, basically the frequency of oscillations can be controlled by applied voltage, and if this Varactor diode is used inside this voltage control oscillator, then capacitance of this diode can be changed by applying voltage, and in that case it will help us to change the frequency of oscillation by applying the voltage or by changing the applied voltage. It is also used in parametric amplifier as a significant component or the main component. We will discuss about this parametric amplifier in this course. Okay, so at that time it would be clear how this Varactor diode is used as a significant component in parametric amplifier. So what we discuss in today's class? So in today's class we have discussed about one of these solid state microwave component, which is the Varactor diode, and it has a speciality that its capacitance value is changed if we vary the reverse bias voltage. And one of the most important thing that we have to note that this diode is always operated in reverse bias condition. This diode is also known as a variable varicap or volt cap. ओके, सो आई होप कि आज के लेक्चर में जो हमने डिस्कस किया दैट क्लियर टू यू. ओके, so let's stop here. We'll discuss other aspect of this course in our next video lecture. Thank you very much.